In a two-way ANOVA, let's just think about what happens, say an ANOVA versus say a t-test. And when I say a t-test, I'm obviously speaking about a two-sample t-test. Well, both of these begin with some sort of measurement. And you want to think about this measurement being quantitative. Hopefully I can spell quantitative. Haven't had a lot of coffee yet. Now, if we want to look at the difference of this measurement, over two populations that are independent, then we're going to run a two-sample t-test. And again, just as a review of previous video, if we are certain that the population variances are equal, then we would run a pooled t-test. We would combine in a real fancy way the variances and come up with a pooled within variance. If we can't justify that we have equal variances, then we run an unpooled t-test. So let's say that we come in and we've got more than two groups. And we've got a third group, or possibly even a fourth group, or we can generalize this into K groups. Now, if we have that, we're going to run an ANOVA. So, guys, just a straight one-way ANOVA. Starts out with a quantitative measure. So some sort of quantitative measurement. And if you just, as an example, you want to think of something, think of an ACT score. Now, what if we want to take a look at the difference in, I don't know, ACT scores across a region. So we want to look at Northeast, Southwest, and let's back up here. Let's take this into four regions. So we've got Northeast, Southeast, Southwest, and Northwest. Now, I have no reason to believe that ACT scores would be biased across region, but nevertheless, if we wanted to compare ACT across the four regions, we could do so. And we would do this using a one-way ANOVA. Now, a two-way ANOVA works pretty much the same way. We start out with a quantitative measure. But we want to bring this into multiple layers. So we would first want to examine the differences across some factor A, and then we would want to look at this across some factor B. Now, let's say factor A has A groups, factor B has B groups, so we would be running a two-way ANOVA, and we would call this an A by B design. For some reason my pen doesn't want to work down here. Okay, so let's just let's scratch that. So it's going to be an A by B design. So for example, let's say that we wanted to look at oh gosh, I don't know, it's kind of hard to come up with something on the fly. Let's say that we wanted to look at quality of TV signal. And we wanted to look at this first of all, for DirecTV and Dish. Now, if that was the end of the game, we would just run a a two-sample t-test and go with it. But let's say that we want to look at this across region. Well, what we have here is we have a two-way Anova because we have two factors. Factor one is obviously the manufacturer or the service represent oh wow, the service provider, and the factor B would be across region. Now, guys, eventually we're going to come in and we're going to do something called ANCOVA, which actually brings in a covariate, which can be quantitative or categorical. Typically, it's quantitative, where we control for things. But we need to learn two-way Anova really well before we start getting too fancy. So, guys, what we would do here, we have 2 levels of provider. We have 4 levels of region. So we would run a 2x4 two-way Anova design. Now, a couple of things going on, actually 3 things going on. The first thing we want to look at is we want to be able to look at if there's a difference from DirecTV and Dish. The second null hypothesis that we'll test will be across region. The third thing that we'll want to test is that the interaction is not statistically significant. Now, there's a kind of a fancy way to state this that really probably won't make much sense right now, but hopefully it will when it's all said and done. We could say that the mu of ijk is equal to the mu, how do I want to put this? That's not what I want to do, I don't think. No, we want to, let's do this, ij dot I dot j I, yeah, I was having a bad day here. I dot k and dot jk, and let's go dot dot dot. Now that'll become clearer once we get into the to the calculations. We're really gonna break this down into a lot of we're going to fine tune the process, and because once we're going to conduct ANOVAs, we're going to do so using R. But I think I feel very confidently that our potential to understand those outputs better is directly tied into understanding the calculations that drive the outputs. So this will become hopefully clearer as we go along. Okay. So ultimately, what we're looking at when we go back and look at this, again, I think the first one is obviously clear, and I think the second one is obviously clear. But you know what? There's a possibility that maybe DirecTV works really well in the Southwest. Or maybe there's a possibility that Dish doesn't work well at all in the Northwest. Well, that's where we get into the interaction and allow not only our comparisons of DirecTV and Dish and Northwest, Northeast, Southwest, and Southeast to be done. It allows us to come in and look at the interactions. And you can imagine why this would be very important in education. You look at something that may be geared at improving instruction. It would be easy to look at looking at multiple layers with the experimental control group and possibly even who knows, personalities of instructors or past grading practices of instructors. So there'd be all kinds of possible combinations for the for Two-Way Anova to be applied. All right, gang. Let's get into the calculations, which is really the purpose of this video. And what we seek to do here is we seek to look at the error decomposition. And really this is just a way of looking at how the sum of squares are partitioned out for the model. So ultimately we're going to have a total sum of squares. And this is going to be the sum of squares for factor A plus the sum of squares for factor B, plus the sum of squares for the interaction, plus the sum of squares for the error. Ultimately, what we'll want to do is we'll want to put this information in an Anova table. And guys, the Anova table, hopefully you remember this from back in 5500, is we will have factor A, factor B, the interaction, and the error. Now there will be a total line down here too. But we really don't worry that much about the total, so I'm just going to leave. I'm going to leave that blank. Okay. Now the first thing we'll want to do is we'll want to partition out the sum of squares, and I'm going to give you all of these later. Then we would divide by the degrees of freedom. So it turns out that the degrees of freedom are just the factor levels of, well, I should say the degrees of freedom for A. Or the factor levels minus 1. Let B be the factor levels for factor B, so that'd be B minus 1. The degrees of freedom for the interaction are always easy to remember. It's just A minus 1 times B minus 1. And guys, the degrees of freedom for the error term are AB times n minus 1. Now, everything's pretty clear so far, but what's this n represent? We let n be the cell count. And when I started this, way back when, I said that what we're looking at, gosh, it's been a long time, we're looking at a balanced design where we have equal n. Now these calculations are crazy enough. If we get into a situation where we don't have a balanced design, they get even crazier. And we'll definitely take a look at that. Well, guys, you should know from there that the mean square term comes in next. So for example, this would be calculated by taking the sum of squares for A divided by the degrees of freedom for A. And well, it's obvious the mean square for the others would be calculated the same. Now, when we get into the F calculation, I don't know why, but I've got a dead spot on my iPad where it will not allow me to write, and that's just annoying. All right, so we've got A, B, interaction of A and B, and we've got the error. And when we get into the calculation for F, which is the test statistic, what we're going to do here for A is we would take the mean square for A divided by the mean square for the error. Similarly speaking, for B, we'd have the mean square for B divided by the mean square for the error. For A cross B, for our interaction, mean square for the interaction divided by the mean square for the error. So we end up getting 3 F statistics here. We'll get an F statistic for A, for B, and for the interaction. The p-value, so we'll end up with 3 p-values. So the p-value is going to follow an F distribution with degrees of freedom, again, for the first term. A, no. A minus 1, and AB times n minus 1. So it's going to follow the F distribution for the degrees of freedom for the F statistics that we're actually making the calculation of, and this will be the degrees of freedom for the error, which will always go in this in that place. So I'm going to illustrate some of this. Now comes the fun part. The fun part is actually looking at the formulas for each of these. And I'll tell you right now, they do get a little bit crazy, okay? So first of all, the sum of squares for the total can be found by taking the sum from I equal 1 to A, J equals 1 to B, and K equals 1 to N. So you're going to see consistent notation here in that I'm going to use I's, J's, and K's for my A factor, B factor, and my cell count N, respectively. So to find the sum of squares for total, we're going to use this. Now that's just ugly, okay? But really all that this is doing is it's taking the sum of, and we're using, of course, multiple summations, so we'll need to review that. But really we're just taking the sum of each cell response minus the grand mean squared. That's all we're doing. All right, gang, let's go on to the next thing. That was so much fun. let's see what the sum of squares for the factor A looks like. Well, first of all, we're going to take the cell count times the factors of B. We're going to run this from 1 to A. And we're going to have this expression. Now, this stuff right here just says we're going to let I, again, run from 1 to A, but we're going to hold the J and the K constant. So they're not going to vary in our calculations. But guys, at the end of the day, what this really tells us is we're just taking, obviously, N times B times let's see, the sum of the row means minus, of course, the grand mean and this is all squared. Alright, now this is again assuming that we've got factor A in our rows and factor B in our columns. Alright, sum of squares for B. As you would probably think, it's N times A times the sum from, guys, don't let me get sloppy on these I's and J's. And all we're going to do here is we're just going to let the J's vary. Now, putting this in lay terms, we're going to take N times A, but we're going to take times the sum of the column means minus the grand mean squared. Well, guys, got the interaction. And the interaction is we're going to do a multiple summation, so we're going to take N. So I equal 1 to A equal 1 to B. And I'm going to run out of plus that. Is that right? Yes. Yeah. All right, cool. All right, gang, let's put this in lay terms. What we're doing here is we're taking N times the sum of This part is going to be the cell mean. This part is going to be the row mean. This part is going to be the column mean. And this part is going to be the grand mean. And this is all squared. Okay, now is that right? Just questioning myself. Okay, the ij is going to range, we're holding k constant, so that's going to allow, look at the means of all of the cells. Good. And this is clearly going to be the row. Okay, yeah, cool. All right, so good deal. All right, so n times the sum of, take the cell mean minus the row mean minus column mean plus the grand mean, quantity squared, and then go for it. Now, one final sum of squares, and this is the sum of squares for the total. And wait a minute, I've already given you that, right? What are we lacking? Yeah, okay, not bad. We need the sum of squares for the error. And the sum of squares for the error is just this. And putting that in lay terms, this is the sum of, so this is going to be our cell measure. Minus the cell mean squared. All right, so that's going to take a tremendous amount of work for the error, isn't it? So, guys, let's run through this. So what I've done here is I found an example. And I took a picture of it. I got it in a book, and I just wanted something, really just some numbers to motivate this. And the picture I took out of a book dealt with this illustration. So you can see that we have a 3x3 design. It's a, obviously a two-way Anova. 3x3 design because factor A has 3 levels and factor B has 3 levels. And to be consistent with the calculations that we're making in terms of rows and columns, I've set up factor A in my rows and factor B as my columns. Now notice in this case that n is equal to 4 because every single cell count, every single cell measure has, I'm sorry, every single cell count has 4 measures. Now the next thing I did is I put this information in an Excel format or an Excel file and put it into CSV format. Again, it's more seamless to get data from Excel into R using CSV. At least that's my experience. So, for example, if we come down here and just look at like this measure of 36.3, we'll see that's from A1 and B2. So go back to your table. So go to 36.3, and you can see again factor 3 and or A3 and B2. Now, what I want to do next is I want to get this information into R. So that's going to be easy to do. Remember, first thing we need to do is set our working directory. The next thing I want to do is get my data. And I forgot what I called this. Saved it on my desktop. I called it Two-Way. And before I get too crazy, I don't want to forget to attach the data. If I don't attach the data, I can't do anything with it. Now, you know, everybody, you know, obviously likes to look at their data. So what we now want to do is we want to come down, be able to come in and do the cell means, row means, column means, and grand mean. So I want to go back to the blackboard here and give you an indication of what we want to accomplish using R. So I want to come in the means. Guys, I want to get totals. Well, this is completely annoying. Pretend I wrote total down here. Okay, again, for some reason, it's not happening. And guys, here I want the grand mean. Alright, so let me show you how to do that easily in R. First thing that we can clearly do is, again, notice that we have our measure, and we have our measure across factor A and factor B. Okay, so the first thing I want to do is make sure I don't get too sloppy here. I don't think that R will see this as anything other than a factor because of the letter. But what if we just had this as like 1, 2, and 3, and maybe this is 4, 5, and 6? First thing you need to do is make sure that R knew that this was a factor. So what I may call this, I might call it factor A, and I'm going to call this fact B. So I'm going to let R know for sure that these columns, factor A and factor B, are to be treated as categorical data. Now again, that wasn't going to be an issue the way I've got this laid out. But guess what would happen? The first time we run into a situation where this variable is categorical, but it was coded as 1s and 2s. You know, we often do that with gender. Codes gender as 0s and 1s. If you forget this right here in that situation, then you're going to get a useless model because it's just going to be incorrect. Now, the first thing I want to do is I just want to do mean of measure, which is going to be my grand mean of 36.275. Now, guys, what I'm doing here, is, let me just run back and show you. What I'm doing here is I'm going to fill in the information with the cell counts, the cell means, the row means, and obviously the grand means. So I'm going to do that for you here. All right. Now, to find the row means, what I'm going to do there is I'm going to do T apply, and I want to do my measure over fac A, and I want my function that it calculates to be the mean. Now, when I do that, I get my means across A1, A2, and A3. So I need 32.75, 39.79, and 36.28. I'm just going to round these things to 2 places, which should give me a pretty good degree of accuracy on my calculations. So again, just make sure everybody's clear here. That's what I just filled in. Now, the next thing I want to do is I want to come in and find my column means, and it should be pretty clear to you that what I need to do here is do the same thing, but do it across factor B. So guys, B1, my column mean is going to be 34.99, 35.38, and 38.46. All right. Now again, just make sure everybody's with me here. This is what we got. Now what we need to do is we need to come in and find the cell counts. I'm sorry, the cell means. And that actually becomes a little tougher, not much. What you have to do here is we have to do T apply, and we're still going to do measure. But what we do next is we do list of fac A across fac B, and then we do function equals the mean. Now, guys, when you get that, you're going to find the cell means for each of the 9 cells. So A1, B1 is 31.45, 31.35, 35.45, 39.85, 38.83, 40.70, 33.68, 35.95, 39.23. All right, gang, what we've done now is we have filled in all the means that we need. Now, let's make one of the easier calculations, and that's going to be the sum of squares for A. You guys remember the sum of squares for A is found by taking n times B times the sum from I equal 1 to A. To get this. Now guys, if you go back and think again about what I told you on in lay terms, what this finds, we take n times b times the sum of the row means minus the grand mean. So our calculations here are going to be n, which is, I forgot, is that 4? Pretty sure it is, right? Yeah, we have 4 measurements in each cell count. There are 3 levels for factor B. And then we're going to get into the, for I equal 1 to A, let me go ahead and, this is clearly 3, because there are 3 levels for. So we're going to come in for, first of all, for the Y bar for when I is equal to 1. So we're looking at what? The first row. So 32.75 minus the grand mean of 36.27 plus 39.79 minus the grand mean squared plus 36.28 minus 36.27 squared. And guys, I'm going to leave the calculations for you. Have fun with that. Sum of squares for B. How are we going to do sum of squares for B? Well, it's just going to be n times A. This is going to be so guys, again, A is, N is 4, B is 3. So we're going to run out the columns, so 34.99 minus 36.27 plus 35.38 and finally 38.46 and again, have fun with that. All right. Now, next thing I want to look at is the sum of squares for our interaction. And wish I'd written this stuff down. Let me just go ahead and we know that n is 4. And the interaction gets really, really, really ugly. quantity squared. So we're probably not going to do all of these. This is going to there's going to be quite a few terms here, but let's just go ahead and get started. So this part right here is going to be the cell mean. This is going to be the column mean. I'm sorry, the row mean. This is the column mean, and that should be plus. Guys, make sure you notice that should be plus. I wrote that wrong the first time. So first entry, we're going to have 31.45 minus the row mean of 32.75 minus column mean of 34.99 plus 36.27. Plus dot dot dot. The last entry we would have there would be 39.23 minus the row mean minus the column mean plus the grand mean quantity squared. Okay? Now, we've got to find, we found the two main effects, and we found the interaction. If we just find one more, we're going to be able to find the others. Because, you know, think about it, we need 5 terms. The A, sum squares for A, sum squares for B, sum of squares for the interaction, sum squares for the error, sum squares for the total. If we know four of those, we can clearly find the other one. I really don't know which one's the easiest to find from here out. They all require a lot of work. I would probably just go with the sum of squares for the error. No reason. The sum of squares for the error and sum of squares for the total both require you to do triple summations. So let me take care of this. And see if I can get this written in here. Yeah, I'm running out of space. Running out of space. That's going to drive me nuts. I can't handle that. You know me better than that. Can't do it. Sorry. Now, what are these terms going to look like? Sum of squares for the error. This is just the cell measure. So this is going to take each individual measurement minus the mean for that cell. So this is going to get just completely and totally ugly. And we're going to have a lot of things to calculate here. I don't think the sum of squares for the total will be any easier other than, you know, I don't know. I'm starting to think to second guess that. This may be the hardest because the sum of squares for the total is just the cells minus the grand mean, right? Actually, I think that's going to be a little bit easier. So anyway, what we would do here, we would go back to our counts. And we're going to take each measurement. So the first measurement is 34.2. Minus the grand mean, which I forgot, 36.27. Plus let's go back to final measurement would be the 36.7. So quantity squared. So yeah, that's going to be a lot of a lot of calculations. I would think that there would be some way that we could do this information in R. I don't know. It looks like there could be. Trust me, guys. The homework assignment I give you will be much smaller than this. Okay, guys, I guess that's really all I've got. I just wanted to run through this with you. The next video, what we'll actually do, I'll tell you what. How much time have I got here? I think I've gone over quite a bit actually. I'm trying to keep the videos at about 50 minutes, and you know how that goes. 50 minutes for Darbro means 2 hours or something. So guys, let's end this, and I think what I'll do next time is we'll come back in and I want to run through one of the illustrations with you. So guys, keep your notes handy on this, and have a good one.